All right, the super cool world of simple harmonic motion is if we can figure out a k value for any system, we can substitute that k into our general simple harmonic motion equations. So after some force work, we figured out that for a pendulum, it follows F equals Ks with a k of mg over L. So all those crazy equations we came up with in that other proof, we can use those for pendulums. We just have to substitute in mg over L. So for example, our time period equation that we came up with in our other proof, t equals 2 pi root m over k. For a pendulum, we know that k equals mg over L. When we substitute that into there, I'm going to let you double check my algebra because this is a common goof up. Since the k is on the denominator, it ends up canceling m and flipping over, we get L over g. Now it turns into a plug and chug question. We know 2 pi, we'll just plug that into our calculator. For this particular question, the L that I made up was 1.5 and the g is 9.8. What's kind of cool is the amplitude factors out, the mass on the end of the string factors out. None of those things matter, just the L and the g. If we had a pendulum on the moon, it would have a different time period, but a 1.5 meter pendulum is going to have a time period of, I carried an extra decimal, 2.46 seconds. That assumes that the angle is small. For this one, the amplitude 0.3 centimeters, so 30 centimeters compared to a 1.5 meter radius. That matches our condition, so we're good to use our equations. The second question, its maximum speed, is kind of similar to the first. From conservation of energy, we had a general simple harmonic motion equation. Vmax is m over k. Oops, I did that backwards. Vmax is k over m multiplied by amplitude. For a pendulum, k is mg over L. When I substitute that into that, since the k is on the numerator this time, the m's cancel and the g stays on the numerator, we get g over L multiplied by amplitude outside of the square root. Now that we've done the substitution, it's another plug and chug. 9.8 over 1.5 in this case, and the amplitude that I made up was 0.3. Cranking that out, I get a maximum speed of 0.77. Our third question, a position after a specific amount of time. Because it's given us a specific time, that's going to have to ring an alarm bell in your head that we have to use. For time, we use the tricky trig. This is a position question, so the tricky trig we're going to use is x equals a cos omega times delta t. Omega was that weird rotational velocity thing. It's related to the time period, but more importantly, it's related to k over m. And for a pendulum, we know k is mg over L. When we sub mg over L into there, since the k is on the numerator, after the m's cancel, we're left with g over L. So that means our function for position at a specific time for a pendulum is a cos root g over L multiplied by the time we're curious about. For the question I made up, I was curious about 3 seconds. Now it's plug and chug again. Now what I found is rounding can really blow up these tricky trig equations, so if you don't agree, it most likely is a rounding thing. It's a tricky trig equation because you have to be in radians. So if you're in radians, if you're using these numbers, we should kind of agree. When I crunch it out, I'm getting positive 0.05 meters. If you got something a little bit different, if you did the same steps, it's probably okay. It's just a rounding thing. Maybe carry extra digits when you do the root 9.8 over 1.5. So the cool thing about pendulums, all those equations we took the time with to come up before with that crazy reference circle projection thing, all those equations will work for other systems like our pendulum. We just have to sub in our expression.